Okay, here's part 2 of this lecture covering the torque that is exerted upon a loop of current when placed in a uniform B field. We're going to take a look here specifically at the energy transfer. Before I do, however, let me clarify a couple of points from part 1. First of all, we have mu once again. Okay, mu is actually called a magnetic dipole moment. I just forgot to say the word dipole. And once again, it's equal to I times A, where A is the area of the loop. However, with this simple demonstration wire that I have right here, it's a single piece of wire that has been looped upon itself a number of different times. Okay, the number of loops associated with this wire is referred to as the number of turns, and it's referred to also as capital N. So then therefore, if you have multiple loops associated with the wire, the magnetic dipole moment is equal to I times A, but we also have to multiply it by N, where N is the number of turns. Okay, that's just an added detail here associated with the dipole moment. You're looping a wire upon itself in different times. Okay, now let's go ahead and get to the energy transfer. Okay, as you'll see, this is analogous to what happens when you take an electrical dipole moment and you place it in a uniform E field. Okay, same idea here. This is the magnetic equivalent. Okay, so imagine that I do the following. So let me go ahead and use this to demonstrate. Okay, and then here is the mu vector tilted on an angle, let's so. Let's say that I reach in and I take the loop of wire, which is right here, and I rotate it from some angle, I'm going to call it theta 1, to another angle like so, I'm going to call it theta 2. Okay, let's calculate the work done by the field when I do that. In order to do so, however, I have to be really careful here with the directions in this calculation. What we're going to define by definition is that out of the board will be the positive direction associated with a rotation, say like this, from a theta 1 to theta 2. However, the torque itself from part 1 of the lecture, if you recall, is into the board. Therefore, I'm going to have to make it negative for that reason. All right, so let's go ahead and write the magnitude of the torque then as a negative number. That is negative mu b sine theta, like so. And now let's set up our integral calculation from one angle, theta 1, to another angle, theta 2. Let's first of all calculate the work done by the magnetic field in doing so. All right, so the work done by the magnetic field is going to equal then the integral of tau d theta. That's going to be the integral from theta 1 to theta 2 of this guy here. Like so. Okay, integral of negative sine is positive cosine. Like so. Okay, and then we plug in our two different angles, and then therefore the work done by the B field is equal to the following quantity. Okay, take the negative of this to get the work done against the B field. Okay, so the work against the B field will be the negative of this, so just reverse the terms. Like so, and then once again, notice the cosine. So at what angle is this quantity mu b cosine theta? At what angle is that quantity going to be 0? It's going to be at a 90-degree angle. Now just be careful about what the 90-degree angle is. Don't focus so much on the rectangular loop of current. Instead, focus on the vector mu. So once again, I'm going to point the mu like so, and then a 90-degree angle on the diagram above looks like this. So the rectangle itself is basically lined up with the B field, but don't pay attention to that. Pay attention to the mu vector instead. The mu vector here is at a 90-degree angle. Therefore, cosine of 90 degrees is equal to 0. So now what I'm going to do is I'm going to let theta 1 just be some angle theta, and then we're going to say specifically that theta 2 is equal to 90 degrees. So let theta 1 just be theta, and let's say specifically that theta 2 is equal to 90 degrees. Okay, therefore the work against the B field, which is now the change in magnetic potential energy, like so, is going to be the following. like so. Once again, cosine of 90 degrees for theta 2 is equal to 0. Okay, then at which value, the final value of the potential energy or the initial value of the potential energy, at which value should the potential energy be 0? Well, it's going to be the final value, theta 2, being equal to 90 degrees. So the left-hand side of the expression is going to be final minus initial, like so, and that then equals this quantity here on the right-hand side. Move the negative sign over to the other side of the expression, and then therefore the initial magnetic potential energy at the angle theta is a negative number, like so. There is another dot product that is present here, by the way, just like there was when talking about this for a electrical dipole in a uniform E field in chapter 21. The general expression for the magnetic potential energy, I'll just call it UB now, is equal to the following dot product. This right here is the magnetic equivalent of this, which we saw, once again, back in chapter 21, okay? All right, now here's how you wrap your head around the negative sign. Once again, just pay attention to the mu vector here. Don't pay so much attention to the actual loop of current. Let's say that I start off at a 90-degree angle like so, and when I do, cosine of 90 degrees is equal to 0. Therefore, right here we have 0 potential energy. And then I let go of it. Okay, when I let go of it, there's going to be a torque that's exerted like so, so then therefore the loop begins to rotate. Okay, as the loop then begins to rotate, the potential energy has to decrease, and then therefore the kinetic energy increases because the energy is conserved. So then therefore, because the potential energy is decreasing from a value of 0. Therefore, it has to be a negative number, hence the negative sign, like so. Once again, wrapping your head around the negative sign is usually the trickiest part of this process, okay? Okay, like we did for chapter 21 with the electric potential energy, for magnetic potential energy, you're going to have to commit this expression here to memory, okay? Okay, that concludes here part 2 of this opening lecture on the torque exerted upon a current loop. Part 3, which I'll record at a later date, will have to do with the applications of this. Applications involving various types of analog gauges, such as a voltmeter, such as a ammeter, and a number of other instruments as well. Get to that later on though.